Hi, everybody. Welcome back to Chem 140. We're not going to start with the lecture right now. We're actually going to start with a little talk about the lab. Which means that I need to capture a different window. Let's see here. This one. Boop. That's a little off, but that'll do. Oh, you know what? We don't actually need all of that over there. This is good enough for now. All right. So, agenda items for today at the bottom of the screen here. So, quiz number 2 is due tomorrow. That was on Unit 3, which feels so long ago now that we're in Unit 7, but the units go really quickly for a little bit. That is due, again, Wednesday. That's tomorrow. It will close on Thursday, so make sure you do it by then. Quiz number 3, which is Units 4, 5, and 6, is due Monday the 31st. It will close on February 1st. There is a Unit 7 and 8 quiz, which will go up some point next week. It'll actually be due after the midterm. But questions from the 7 and 8 quiz will be present on the midterm, so it's in your best interest to do it early. I have a special setup for that quiz where it will automatically release the answers after you have done the quiz, so unlike other quizzes where you have to wait until I release the answers after everything is done, that last one it'll release automatically. And then we have lab number 2, which we're going to talk about today. So lab number 2 is a density worksheet. Density we covered in Unit 5. We're going to look at some different ways that we can apply density and use it to determine various quantities or calculate density from various things that we can measure, and so on and so forth. Very, 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 very important. For lab number 2, like 99% of the mistakes that people make on lab number 2 are sig figs related. And it is possible to get a 0 score because you've made so many errors with sig figs. So be real careful that when you are subtracting numbers or you're multiplying numbers, you're doing whatever, that you are checking for sig figs, because I am relentless. I check every box, and if it's the wrong number of sig figs but it's the right answer, you lose half your points for that problem. So be attentive. We care very much about your precision on this. So you're going to do 4 parts to this lab. The first part involves water at an unknown temperature. You're going to find the temperature of the water by measuring its density. So I will give you a volume and a mass, which you'll use to calculate the density, and then you refer to this table. You're going to select the temperature that is closest to your density that you've calculated. You'll notice that all of these densities are quite close. They only change in like the thousandths place or the 10,000ths place as you increase the temperature. Let's see here. Part B is a bunch of solutions that I'm going to have data for. You calculate the density for all the solutions, and then you have to plot the data on a graph. And we're going to show how to do that in just a second. Part C, you're going to figure out the density of aluminum using difference. And then part D, you're going to figure out the thickness of an aluminum foil. And we're going to come back to this formula in just a second. So let's talk about part A. And the worksheet just fell asleep. Hold on. There we go. And you can't see that anyway. So we just cover up everything. That's okay. Okay. So this is worksheet number 1. You can't see because I didn't fit it on the screen. Oh, no. What have I done? Hold on. Down at the bottom there are the tabs for different experiments. So B, C, D, and E. You are going to want to make sure that you answer all the questions on all the pages, because if you skip any, that's no good. All right. So part A is some basic questions about density. Before I give you some, here's the water that we're going to be looking at in part A. That's the wrong thing. So here's our data. So I have a vial plus water. I have a volume of water. And from that information, you have to figure out the density. So how do you figure out the density of anything with a container? Well, we'll go over here real quick. We don't need this, so I'll just shove it up here for a second. When's the lab due? It's due next week. That's in the syllabus. So if I have a vial, so here's the lid of my vial, and here's the vial itself. And then I put water in it. So there's my water. So the mass of the vial includes the lid. If I include water and I figure out its mass, so let's say that this is like 30.0, this is 25.0. If I subtract these two, then this part gets subtracted out because it's the same in both cases, right? And then these would all be in grams or something. So this is called weighing by difference. If you weigh something empty and then weigh something full, you can subtract the two to get the mass of the substance that is inside. And you could do that for any experiment where you might be required to do that in this lab, which turns out you'll be doing that quite often. Okay. Once you know the mass, you can figure out the density with the volume, and you can calculate it to the correct number of sig figs based on the numbers that are reported. So I have a bunch of digits here. Make sure that you are doing the operations correctly, the addition and the subtraction. So part A, you're going to find the temperature of the water. And then down here, I give you a different liquid that is unknown. So I want you to figure out the density of the mystery liquid and then tell me what it is based on these possible densities here. Should you be using sig figs for only the final answer or all mathematical steps? Use sig figs as we have described in the lecture. So all sig fig rules must be applied all the time. If you can do multiple steps together, so like if you're multiplying 5 numbers at once, that's totally fine. Round to the correct number of sig figs after that operation. And then when you take that number and use it in a future step, it has a number of sig figs that come with it based on what you did to it already. So if you use the answer for number 3 and the answer to number 3 has 5 sig figs in its value, when you use it in number 4, you use those 5 sig figs. You don't get to add extra numbers in. You don't get any more extra information just because, oh, I'm using this number for another problem. So can I keep all these numbers? No, you can't because you don't know them, right? They're arbitrary numbers. So follow the rules of sig figs for every operation that you do in this lab. So that's part A. Part B, you're going to do more or less the same thing. You're going to find the density of a bunch of liquids. And then you're going to plot a graph. And this is the part that a lot of students struggle with because they've never used Excel before. Or they've never used Google Sheets. So I'm going to show you how to make a graph. In order to make a graph, we have to plot some data. So I'm going to say 0, 25, 50, 75, 100. Actually, you know what I'm going to do? What I'm going to do is I'm going to make a copy of this so that I'm not doing this in the default worksheet so that you don't get a graph that is full of just random shit in it. So I'm going to make some data here. And then I'm going to assign some density. So I'm going to say 2.5, 2.2, 1.8. I don't know. I'm just making up some numbers here. That's not what I want. All right. Now you're going to notice that even though I typed in 1.22, oops, 2200, look what Google Sheets did to this. It screwed up my sig figs. How do I fix this? I want those zeros. Well, if you take your cursor and you go up here, where it says increase decimal places, it will add extra zeros on the cell that you've selected, or reduce them if you have too many sig figs. If you have too many sig figs, it will round to the place that you have truncated to. So I can do this, and I can do this. So you won't get dinged for zeros on sig figs, provided that you hit that button. So if Google Sheets is trying to truncate out your zeros, you can add them back in using these two buttons up here. Okay, so make sure you use those. All right, so we've got some data, and I actually have the directions right here for how to make the graph, but I'm going to show you how to do that just so you have a visual example to follow in case you need to, because some people do that a lot easier. I need just a second, though. Sorry, I had to address something real quick. All right, so the first thing we're going to do is we're going to go up to here where it says Insert, and we're going to hit Chart. And it should put a big block down that just says No Data. There you go. So we need to tell this chart that it needs to have this data. So over here, in the chart type, the first thing I need to do is I always pick scatter. Oh, you can't see this. It's off the screen. Hold on. Sorry. That part's kind of important. You need to see this part. All right. Over here where it says chart type, you have to select scatter. That's the first step. Always do a scatter plot. No other graph is useful to us in science. Like 99.99999% of graphs you're going to do are scatter charts. So we're going to hit that. And it's going to ask you for the data range. The range is the y-axis. So you hit this button, and you select the data that you want to be the y-axis. So we'll do that. And then what it's going to do is it's going to plot it arbitrarily along the x-axis, how it thinks it's going to go. But we don't have an x-axis. We can add one by clicking Add X-axis, and we're going to select the data to be this stuff. And there you go. Now we've made a graph. Ta-da! See, that wasn't hard at all. You're going to plot density on the y-axis and isopropanol on the x-axis because the dependent variable is the density. The density depends on how much isopropanol there is. The amount of isopropanol does not depend on the density because you could add other stuff and change the density, right? All right. So now that you have your graph here, you have to do a few other things to it because the graph doesn't really tell you much as it is with just a bunch of dots on it. So we're going to go over here to Customize, and here's what we're going to do. The first thing you're going to do is you're going to give your graph a title. So you need to choose an appropriate title. Typing a title of the graph is not appropriate. I'm just doing that to show you an example here. For the titles of the axes, you need to label them with what they are. And there should be a way to do this on here. Oh, it's in chart and axis titles. So you go to chart title. So for the horizontal axis on the bottom, I will call that is the percentage of isopropanol. There you go. And then for the y-axis, which is the vertical axis, we would say density in grams per milliliter. So it is important to put the units on your axis so I know what they are. And so now our graph is more or less complete. The last thing that you want to include on here is, and I always forget where this is. It's not under grid lines. There it is, series. So you go to series, and you scroll down to the bottom here where it says trend line, and you check that. And then after you've checked that, a bunch more options appear. You're going to go down here and say use equation and show R squared. And what this does is it shows you that if your data was actually an equation on the graph, this is the equation it would be. Negative 0.0129 times x plus 2.5. Your data conforms to that line. How well does the data conform to that line? 0.999 out of 99.9% confirmation, basically. R squared is a statistical value that tells you how good is your data. So, like, if I change this number, and this is kind of the power of Excel, I can change this to whatever I want. Say I got 6.0000. Whoops, now my data doesn't conform to a line very well anymore, right? Because one of my data points is way up here. So now Excel thinks, this is the best line. How well does it conform? 30%. 30.3 or so. So there you go. So Google Sheets, Excel is the same thing, will plot all your data onto an equation when you hit that trend line button. And also you want to check the R squared on there. These are functions that will be important in 161. For your graph on this report, I just want to see that they are included so that I know that you know how to access those functions on here. If you're taking 161, we're going to plot data a lot more often, and you're going to use the equation generated to calculate unknowns. In this case, you are also going to calculate an unknown because you have an unknown up here that has an unknown amount of isopropanol in here, and it will have some density. You can use this chart to visually estimate that by saying, oh, my density was this, so therefore it must be this percentage of isopropanol. That's good enough, but if you'd like to use the equation, you can also do that. The equation is a better and more accurate way, but for our purposes, visually doing it on here is fine. When you're done, make the graph nice and big, and you're all set. Very important, regarding the graph, if your graph does not show up when I open your form, you don't get credit for it. I have tested that if you do the steps in Google Sheets like I've just done here, and then you download the file and then upload it to Canvas, when I get it, I will see your graph. If you deviate from the directions that I just showed you and say, well, I know how to make a graph, I'm going to do something different, or I'm going to use Excel or whatever. Again, if it doesn't show up in my Excel sheet when I open your file, I give you a 0 for that assignment. Okay, so do this at your own peril using some other worksheet or format or whatever. You have to use Google Sheets to ensure that I will get it. Any other mistake is generally operator error. So if the graph does appear but there are mistakes in it, it is usually because you did not follow one of the steps. And then I deduct points for that. Okay, so make sure you include all the things that I've shown you. And make sure the graph is somewhere in the blue box. Like, don't shove it over here. Oops. Don't shove it over like there. I won't see it when I grade because I'll be like, oh, you don't have a graph. Okay. It's got to be in the blue box. All right. Part C and D are more or less just more applications on density and doing stuff with aluminum. So Part C, you're going to figure out the volume of aluminum pebbles by dropping them in water. Well, if the volume of water that you have is this before you added them, and it's this after you added them, you can do simple subtraction to figure out the volume of the aluminum. Part D requires the density of aluminum. This value right here in Part C that I have bolded can be used in Part D. And we're going to need to go back to the formula worksheet for this real quick. Let's go back to this right here. For Part D, I give you a bunch of formulas. Oops, I went all the way to the bottom. There we go. What I'm going to do actually is I'm going to go over to this screen real quick, and I'm going to derive this for you so that you've seen it. Your task for Part D is to figure out the thickness of an aluminum sheet. An aluminum sheet can be treated as a rectangular prism with length L, width W, and thickness T. In other words, its volume is just those three things multiplied together. Now, we also know that the density of this, which is made of aluminum, is its mass divided by its volume. we can put both of these things together to get the following expression. The density of the aluminum is equal to the mass divided by the volume, which is just simply this. I'm substituting in the volume into the equation. And now what I can do is I can solve for the variable that I need to know, which would be this. Thickness equals mass divided by length times width times density. So there you go. If you know the mass of the aluminum foil, its length, its width, and its density, you know the thickness. Now, what are the units going to be for this expression? Your job is to figure that out by putting in all of the things into the equation and seeing what cancels out. And I'll give you a hint. The density of this is going to be in grams per cubic centimeter. So you're going to get a specific thickness out when you do this analysis. When you have done that, you're going to enter your answer into the Google Sheet and then convert it to various forms as I ask you to. So centimeters, meters, micrometers, and nanometers. Nanometers. You're going to put the answer in there once you've calculated. And then finally, once you've done all these parts, we have the analysis questions right here. These are just summary questions that, hey, you did all the lab experiment. Go back and look at your results and then tell me something about it as I ask in these questions. Very, very important. 2 things to know for this lab. Number 1, any box that does not have units immediately after it, you must include your units as part of your answer. For example, here it asks you, what is the density of water used? If you type in this, it's wrong. If you type in this, that's much better. Okay? So if you do not include the correct units, I flag it wrong. Okay? So be careful. If the units are already attached to the end, you don't need to type them in. Oops, I was trying to type in a degree symbol, and I hit the wrong button. You do not need to do this, for example, because the units are already shown. So in this case, just the number is appropriate. Okay, so beware of that, because a lot of these boxes do not have units in them, and you need to include the units in them. And then some of them do have units after them, and you do not need to include the units there, okay? So be cognizant of the context of the problem and put the units in where they are needed, and you can omit them where they are not. Finally, in the questions over here, if I ask you to explain how you got your answer in 1 or 2 sentences, I want you to tell me why your answer is as it is. Don't just say, I followed the directions as discussed in the lecture. I want you to tell me why you did that. Explain the lecture topic to me. Why? Because how do you find the density? Do that thing. How did you get your answer? Tell me what you did to get your answer. You need to tell me that information. Note that some questions, like this one, do not tell you to do that. In that instance, giving me just the value of the answer is sufficient. So if the answer was 44 and you typed in this, if you just typed in that and that's the correct answer, that's all you need to do for that problem. For the other 2 problems above here, you'll see it says describe how you got your answer. You do need to describe how you got your answer to get full credit. Okay? So again, make sure you're following all the directions. Will the assignment be posted on the Canvas calendar? Yes, it will. It just has not been posted yet because I have... Oops. Sorry, I had to hit a button. I have not formally assigned it yet. I have now formally assigned it, so it will show up on the calendar after the lecture today. If you have any questions about any of that, let me know. Happy to answer them. The assignment will be due 1 week from today, which is Tuesday the 1st. All right, I got to get back to the right screen here. I do not wish to remove 14 items, no. No, I would never want to do that. I was clicked on OBS. I almost deleted everything. All right, there we go. All right, Unit 7 is about atomic structure. In Unit 6, we talked about matter and some various ways we can compartmentalize and categorize it. In this section, we're going to be zooming in much further to talk about what matter is made of, and that is the atom, which I'm sure everybody has heard of what an atom is. So let's conceptualize that here. Let's suppose that I gave you a sheet of copper. Here it is. And I want you to take that sheet of copper and I want you to split it in half. And then I want you to do that again. And again, and again, and again, and again, and again, and again. Over and over and over and over and over and over and over. At some point, you will not be able to split the piece of copper in half anymore. It will no longer be copper if you do that. That tiniest piece of copper is what we're going to call an atom. An atom is the smallest possible chunk of matter that resembles an element off the periodic table. If you chop down smaller than that, you either get some other atom because you've cut a fraction of it away, or you get subatomic particles, which are not elements. So that's going to be our goal here, is to discern what this limit is, and we'll call it the atom. Atoms are so small that I can't even imagine this. One atom of gold has the mass shown on the screen, 3 times 10 to the minus 22 grams. It would take 3 times 10 followed by 21 zeros to give you enough gold to equal just a paperclip. Now, on the right image there, you can see I have found a picture from a scanning electron microscope, and each of those little orb-like dots is an atom of gold. So we actually have technology to visualize atoms at the atomic level to this level of resolution, which is, to me, super impressive. To somebody who is probably new, probably not all that impressive, but I mean, to be able to see something this small, I think is just incredible. So atoms are extremely tiny. They are also extremely empty. And that's very interesting. Inside an atom are 2 parts. The first part is the nucleus. The nucleus is extremely dense, and we'll get to that in just a second. The electron cloud, where electrons live but do not encompass entirely, is some 10,000 to 100,000 times bigger. So what this means is that an atom is actually 99.999% empty. There is nothing in there. Which is very interesting because we are made of atoms, so we are also 99.999% empty. I was debating on how long I should let the little existential crisis gap there go. Yes, you are 99.9% empty. You can go tell your family that. Mom, my chemistry instructor said I'm 99% empty. And he's true. Because you are. I am too, right? Because all of the matter in the atom is focused in the nucleus. Everything else in the electron cloud, there's like a few electrons out there, and then the rest is an empty void. Yes, even Maya is empty, who is meowing at me from the hallway. Now, if you have your periodic table handy, which I don't remember if I copied p-table for you, so we'll just do this. So there's p-table. You can click on that and go to a periodic table. That periodic table lists all 118 different types of atoms, and those are the elements that we discussed in Unit 6, where we categorize stuff into elements and compounds. For any given element on the periodic table, all atoms are identical in terms of their chemical properties. Every single sodium atom reacts the same way. Every single copper atom reacts the same way. But sodium atoms and copper atoms react differently towards each other. Or in relation to each other, I should say. Now, are they physically identical? We're going to talk about that later today, and the answer is no. There are some minor differences, but for our purposes in chemistry, all these elements are unique, and all atoms within the element are identical. Oops. There we go. Now, when you mix multiple atoms together, what you get is a compound. So we talked about compounds in Unit 6. Compounds are combinations of multiple atoms together. For instance, if I take hydrogen and oxygen, I can make water, or I can make hydrogen peroxide. All water molecules behave the same. All hydrogen peroxide molecules behave the same. But water and hydrogen peroxide are different from each other. One of those is refreshing. The other one will kill you if you drink too much of it. In fact, H2O2 is super, super reactive to the point that it's almost harmless. But it will cause chemical burns, obviously, if you expose yourself to it to a high concentration. Now, when you do chemistry, which is the combination of matter with other matter, you create new compounds. But those compounds do not just come out of the air. Because atoms are indestructible, all you're really doing is rearranging things. So if I add something that has copper in it, and oxygen in it, and nitrogen in it, to something that has phosphorus and oxygen and nitrogen or whatever, my products are going to be some rearrangement of those atoms. I will not suddenly have calcium or iron in it, because if I didn't put it in there, I can't have it. I am only going to be able to rearrange the substances that I put in there. So when we actually do get to chemical reactions later on, you'll notice that, oh, what goes in must be what comes out. And that makes sense, right? For our purposes, atoms are indestructible. They will not be broken down into smaller pieces to create random other elements. Now, can this actually happen? It turns out the answer is yes. Atoms are not indestructible in reality. Some of them are radioactive, and they change their identity. For example, a lead atom can radioactively decay into, and I'm trying to get my periodic table to find this, a mercury atom. So you can turn lead into mercury by having lead be radioactive, and then it loses an alpha particle and it will turn into mercury. So that is a thing that can happen in nuclear chemistry. However, it is not common in the laboratory that we're going to be looking in. So, like, we're not going to give you anything radioactive that would decay, obviously. So, we'll talk about that briefly in 163. In chemistry, the two types of compounds that we're going to be exploring are these two. Molecular compounds and ionic compounds are very different from each other So much so that we spend a whole unit in chapter 4 of Chem 161 talking about ionic compounds. And then we very briefly talk about molecular compounds in terms of their geometry. It's been a while since I've done 161, so I want to say that it's like late chapter 4 and then early chapter 5 or something like that. Molecular compounds are discrete. What that means is that I have independent... Oops, I gotta select the pen here. And that's not a color I can see. So what that means is that I have individual clusters of atoms that are isolated from each other. And I'm trying to just circle these without bonking into other things. These are all independent molecules. They can spin, rotate, move, however they want to. Whatever energy they have, they will bounce around. Isn't there something about how molecular compounds are two nonmetals and ionic compounds have metals? You're right. That is a thing that happens for those compounds. We're not going to introduce that just yet. That's going to come up in, let's see, probably Unit 9 and 10. So after the midterm, we're going to talk about that. I'm just introducing the types of compounds here for when we see them later. But you're right, molecular compounds are just nonmetals. Ionic compounds have metals in them. The differences that I want you to realize here are that molecular compounds are independent, discrete things. So, for example, if the formula is H2O, I have H2Os floating around. And they exist independent of each other. Down here, this compound is NaCl. However, I do not have NaCls floating around in the lattice. An ionic compound is a repeating array of ions, and the formula we assign is the simplest repeating pattern. For instance, and this is a simplification, but I use it anyway. Right here, this would be an NaCl cluster that you could copy and paste, right? If I copy that, I could paste over and over and over in 3 dimensions, and I would generate the entire lattice. Now, obviously, it's more complex than that for more complicated structures such as like MgCl2 or Na3PO4, when there's a lot more atoms. They can't form these just simple repeating blocks. But we'll cover that in 162 when we talk about structures. All right. We're going to talk about those substances in more detail later on. The next term that we want to define is molecule. So if I can have molecular matter, what is a molecule? A molecule is any collection of 2 or more atoms. It turns out almost all matter is molecular. Noble gases tend to exist as atoms flying about by themselves, but all other matter tends towards molecular. Now, I believe I have a bunch of pictures here to just show some examples of molecules. There are many ways to represent molecules. A common method is to color code various spheres where each sphere represents an atom, and then place the atoms in their spatial arrangement that you would notice. H2O is considered molecular if it is solid because of the hydrogen bonds. So, you're kind of getting ahead of us. We're going to talk about hydrogen bonds in 161, not really in this class. H2O is still molecular because there's no actual chemical bond between one water molecule and another. There are attractions, but they're not bonds. So you have discrete individual H2Os regardless of what phase you are in. On the screen, you can see that hydrogen is often colored white, oxygen is colored red, and carbon is colored black. These are standard colors that are used. Sulfur is yellow and phosphorus is orange. Those are more uncommon. Sulfur you see enough of. I don't really see phosphorus that much. Oh, excuse me. Other common colors are nitrogen is blue, and then halogens, such as like fluorine, chlorine, bromine, etc., are often either purple or green. The colors that are selected are oftentimes representative of what these elements are in nature. So oxygen is important for fire, so it gets red. Sulfur is yellow, so it's just yellow. Carbon is charcoal, which is black, so there it matches up. And then hydrogen is a colorless gas, so they just do white. So if you're ever seeing structures that look like, where's my cursor? There it is. If you see structures that look like this later on after this class, those color conventions are generally preserved. All right, your textbook has two categories that you can categorize molecules into. And what we're going to do is yawn. Excuse me. I'm making everybody else yawn too. If you're at home yawning, I sympathize because I'm doing it as well. The first category is going to be the number of atoms in the molecule. If there is one atom in the molecule, quote unquote molecule, we'll call it monatomic because there's only one thing. 2 would be diatomic, 3 would be triatomic, and this goes all the way up to 6 or 7 or whatever you want it to be. But in reality, after 3, it's appropriate to just say, you know what, polyatomic, that's good enough. So, for a given molecule, count how many atoms it has, and you can assign it a category. Monatomic, diatomic, triatomic, a higher order if you would like, or just say polyatomic for more than 3. And then the last category would be what types of atoms are present. Are they all identical atoms, or is there a mixture of different types of atoms? So if you have 2 that are the same, or 2 atoms here that are the same, and that's it in your molecule, we would call those homatomic. There's only one type of atom present in the molecule. Sorry, just sitting here yawning all of a sudden. 2 or more types of atoms would be heteroatomic, where you have different types. So homo being same types of atoms, hetero being different types of atoms. All right, so what I want you to do is categorize my molecules shown on the screen, and I'm going to number them here. So where'd my pen go? Oh, no, it's not working. There we go. 1, 2, 3, 4, 5, 6. So these are 6 different molecules. I put this table up initially because everybody got confused when I didn't have lines separating all these things. And then when I did, they still were confused. So now I just number it. So these are 6 different things. The top 3 are in pictures. The bottom 3 are in formulas. I want you to give 2 labels to each of these. One of the labels needs to be monatomic, diatomic, triatomic, polyatomic. The other label needs to be homoatomic or heteroatomic, okay? Write your answers in the chat when you get them. We'll go over the answers in about 2 or 3 minutes, and then we'll take a break. So see you in a bit. All right, 1 more minute, we'll go over the answers. All right. So this first one, I drew 3 spheres that are all the same color. So, oops. So we'd say homoatomic for that one. And there are 3 of them. 1, 2, 3. There you go, triatomic. For the second one, there are multiple colors. So there are multiple types of atoms present. So that means this is heteroatomic. And then how many are there? There are 1, 2, 3, 4, 5. You could say pentatomic. I'm just going to write polyatomic. For number 3, there's only one, so you have to write monatomic. And something that is monatomic can only ever be homoatomic. In fact, this label for this one is kind of pointless. Because, yeah, if you only have one atom, you can't be 2 types of atoms at once. All right, down here, how many different types of atoms are there? Well, there's C and there's an H, so that's heteroatomic. Heteroatomic. There we go. And then how many atoms are there? Well, there's 6 plus 6, which is 12, so that's definitely polyatomic. Number 5, Br2, there's 1 type of atom, so homoatomic. And there's 2 of them, so we'll write that. And then finally, over here, 2 types of atoms, which is heteroatomic. And then there are 3 different atoms present, so we would say triatomic. All right, there you go. That's how we categorize our matter. So when we come back from our break, we are going to do even more work with matter and understanding what different atoms look like. We'll move on to isotopes and how to notate them. But for now, we will take a 10-minute break, and we'll see you back after that. So, back in a bit. All right, we are back. There we go. All right, I hope everybody had a good break. We're going to continue by taking what we've talked about for atoms and particles, and we're going to put all of our information into a little tiny symbol that will report how many of each particle are in an atom. Now, we haven't actually properly introduced these particles, so let's do that right now. An atom contains 3 distinct types of particles, and the majority of those particles are found in what's known as the nucleus. The nucleus is the tiny, dense center of an atom. Now, this diagram that I've shown here is very exaggerated. The nucleus is not this big relative to the electron cloud. The electron cloud is much, 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 much bigger. But it's drawn like this so that you can see the actual objects. All right. Outside of the nucleus is the electron cloud, and in that region, electrons fly around at very, very, very high speeds. Now, the electrons are not bound to these constrained sort of ring systems. They can actually fly around wherever they want to. So the electron cloud is just the region in which the electrons can be, but the actual path of the electron can be anything like that it wants to be. And as you can see, it eventually carves out a sort of spherical region. So, on the board, you can see that these particles have symbols on them. Those are their charges. An electron is negatively charged, a proton is positively charged, and a neutron is not charged at all. Do electrons orbit the nucleus? Not orbit in the sense that, like, the Earth orbits the sun. The electrons go flying all over the place in random directions, but stay roughly on average the same distance away from the nucleus. So they have a very chaotic path that they follow. And the reason for that is because everything that is oppositely charged is an attractive force, but everything that is similarly charged is a repulsive force. And so everything is pulling on an electron every which way, and it goes all over the place. So it's impossible to describe the path of the electron because there's just too many charges operating on it at a given time. All right, so those are our charges. And like I just described, opposite charges will attract to each other. But like charges will repel. So these two would repel, and so would these two. But these two up here would form an attractive force. Now, what is the purpose of the neutron in the middle there? What neutrons do is they are actually attracted to protons, and they hold them together through what's called the strong nuclear force. The nuclear force is the force of attraction between nucleons, which are the protons and the neutrons. Nuclear forces are beyond the scope of this class, but really what you can think of is that neutrons are like nuclear glue. They hold protons together. If there are too few neutrons, then the protons would repel each other and the nucleus would fall apart. If there are too many neutrons, then they don't stick and they fall off, or they themselves decay, which is a thing that can happen in radiochemistry. Or in radioisotope chemistry, I should say. For our purposes, we're going to assume that the number of protons and the number of neutrons is a number that makes it stable. That's good enough for us. They make the atom fat. Yeah, I mean, they do. They do add mass to the atom. Technically, everything adds mass, but the neutrons do have a purpose, and that purpose is stability. Now, if you have an atom, and we've been talking about atoms all day, atoms are electrically neutral. So what that means is that the number of protons will equal the number of electrons. Now, it is possible to change the number of protons and electrons so that they are not the same. This would be called an ion. And we're going to talk about ions in Unit 9. That's where we're going to start after the midterm. Now, atoms are very difficult to manipulate the number of protons in, because they're in the nucleus and they're all bound together with neutrons. So, unless you have very, 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 very high energy methods, such as like launching, I don't know, launching neutrons into the nucleus or something like that, or even electrons or protons or something like that, the nucleus tends to stay the same. It does not decompose and fall apart unless the atom's radioactive. But generally speaking, most atoms are not radioactive, and they're very stable. They stay this way. The electrons on the outside, however, are very mobile. They are easily added and removed from various places. And so this is where chemistry comes in. Chemistry is just the movement of electrons into or off of an atom. If you end up with a different number of electrons than you had protons, the resulting species is called an ion. And so we're going to be doing a lot of work by turning atoms into ions, or ions into atoms, or back and forth, and moving electrons all over the place. In fact, all of chemistry can be described as just, hey, moving electrons around. So congratulations, you now know the secret of chemistry. I hope it was worth it. Now, on the screen I have a carbon atom. The carbon atom is specifically identified as carbon based on a feature inside it. And that feature has to do with this, the atomic number. The atomic number is how many protons something has. If you have 11 protons, congratulations, sodium. If you have 6 protons, you're a carbon. If you have 10 protons, you are a neon, and so on. The atomic number is always shown at the top of a box on your periodic table. Whether it is on the left, center, or right depends on the periodic table you are looking at. Mine on my desk here has it in the center on the top. There are other things on this box that we will come to later on. We're going to talk about this number at the bottom here, what this means, probably on Monday next week. Because I don't think we're going to get to it today, but who knows? We have, what, 40 minutes? It's possible we'll get to that. So now you know the number of protons any atom has just by looking at the periodic table. So you can associate that number with a symbol. 11 will always be Na. 12 will always be Mg. 1 will always be H, and so on. So let's put together all of the information that we've learned and create a symbology that gives you information about an atom without having to draw a picture of the atom itself. Yeah, it is grams per mole. There is another use for it, which is going to be more practical to us right now, but grams per mole is going to help us a lot more way later. Unit 12, I think, is when we'll start grams per mole. All right, first things first. The atomic number is the number of protons. I'm going to call that this variable here, Z, or Z if you're Canadian. The number a, or the variable a is going to represent the mass number. Now the mass number is going to be how many protons I have plus how many neutrons I have added together. Whereas z is just the number of protons. So there's a little bit of redundant information, but we've done this for a reason. You'll see why in a second. Now, since we're looking at atoms for most of these examples, in a neutral atom, the number of protons and electrons is identical. So Z will tell you the number of electrons there are also. So let's put all this information together. Let's do that. Finally, A is not this number. This number down here we haven't talked about yet, so this is not A. We'll talk about what that number is in just a little bit. All right. Here is what we're going to do to write these isotopic symbol notations. So the first thing we want to do is, I have on the screen curly brackets E. We're going to scribble out the entirety of that symbol and replace it with whatever element we are looking at on the periodic table. The only reason I put the curly brackets in there is because when I had just the letter E, everybody would just write E instead of the actual symbol. And I want you to replace the entire thing with the symbol. So once you have written down the actual symbol, the next thing that you're going to do is, as a subscript in front of the elemental symbol you wrote, you're going to write the atomic number. That's going to be the number of protons. As a superscript before this symbol, you're going to write the mass number. Which is the number of protons plus neutrons. And then finally, if necessary, you could write the charge up here. But for our purposes, if we're just dealing with neutral atoms, we don't have to worry about that. So at that point, we can just celebrate. And this is known as isotopic notation. I have made up this little shorthand. I call it ZAE notation. Nobody else calls it that, though. Let's do an example. I want to work with a sulfur atom that has 16 protons and 17 neutrons. So what is the atomic number of sulfur? Well, it's the number of protons, so I would write 16 right there. And then it has 16 protons and 17 neutrons. What is the mass number? Well, remember that the mass number is protons plus neutrons, which would be 16 plus 17, which is 33. So we write that up there. And there's our result. Oh, excuse me. All right. So now that you've seen me do that, I want you to write the isotopic notation for each of these atoms. Now, I've tried my best to make it like a little puzzle. So I've scrambled up the information as best as I can. You will need the periodic table to answer this. If you could scroll up in the chat, it's up here. Where'd my cursor go? There it is. Or you could just not scroll. There we go. Yeah, it's right here. I want you to write the isotopic notation symbol for each of these. Try to type it in the chat the best that you can. I realize that that's going to be kind of difficult. But we'll go over the answers in about 4 or 5 minutes. So see you in a bit. All right, 1 or 2 more minutes, we'll go over the answers. All right, let's see here. So for an atom with 25 protons and 27 neutrons, I'm just going to go over to this screen. Just to give me a little more space to work with. All right, so 25 protons would be my Z. 27 neutrons would be 27 plus 25, which is 52. So that'd be my A. And now I need to look at the periodic table to find which element is element 25, and that is manganese. So there you go. So there's the first one. The second one we're going to do in the same way. Z is 37, so that'll be my subscript. A is 72. So I just put those numbers in there. I don't have to add them together because I've already been given A. And I got to look up what element 37 is, and that is rubidium. So there you go. There's that one. All right. For the third one, I have to have the same number of protons and neutrons. So I know that the protons equal the neutrons. And that A is 36. So if I add protons plus neutrons together, they must equal 36. And these are the same thing. So I could just substitute them out. Since the number of protons is equal to the number of neutrons, right? And do algebra. Where did algebra come from? What? Yeah, you could do algebra with everything, right? So if there are 18 protons in this and 18 neutrons, that would mean I would write this symbol, 1836. And then whatever the element for number 18 is, which I believe is argon. There you go. And then the last one here. One fewer neutron than protons. And A equals 19. So protons plus number of neutrons, which is however many protons we had minus 1, right? Equals 19. So if you didn't want to sit there like guessing and testing things, there's the algebraic way to do it. So I would say, okay, 10 protons. There's one fewer neutron than protons, so that would be 19. And what element is this? Well, it's neon. So there you go. That's how you're supposed to do those. All right. Any questions? Let me know. All right. Let's talk a little bit more about ions, and that's probably going to be the last thing we do today. We can do isotopic mass on Monday. All right. We have talked about everything on this slide other than this conclusion at the bottom, which is very important. The total charge on any atom is 0. So we did say that the same number of protons and electrons must be on a neutral atom. Otherwise, the charge wouldn't be 0. So the total charge on an atom must equal 0. If it is not 0, then we get an ion. Ions are the result when you have different numbers of electrons than there are protons. Remember that we can only really manipulate the number of electrons easily. It is very difficult to manipulate the number of protons. Some terminology here. If I have an ion that has more electrons than protons, I'm going to call it an anion. Anions are negative. Cations are positive. Cations have fewer electrons than protons. Now, the way that I remember this is if you write out the word cation, the positive's already in there, right? You can see that. The other way that you can remember this is my coworker likes to use this method, is I wish you could see me actually here, because I'm doing the lucky cat thing, where the cat waves its arm. Cats have paws, positive. I'll let that just live in your head rent-free now forever. And yes, it is stupid and it sounds dumb, but hey, whatever helps you remember. So, anions are the other thing. If cations are positive, anions must be negative. Now, the real thing that is going to screw people up here, and I see this every time I teach Chem 140, is that when you are making something positive, it is because you are removing the negative thing. So, if you are taking away electrons from an atom, it gets more positive as a result. So if I have something that's neutral and I remove 3 electrons, its new charge is now positive 3. If I give it 5 electrons, its new charge is now negative 5. So be careful. It's kind of backwards when you are first doing these exercises. But remember that electrons are negative, so you just treat it like subtracting negative numbers, if that helps you. All right, so let's do some examples. I want to write the ion that forms when an electron is taken away from sodium. And I'm going to do this. We're going to just do this the long way. So number of protons, number of electrons, charge. So neutral sodium has 11 protons and electrons. Its overall charge would be 0. But I want to take away... Oops, that's not what I meant to do. I want to take away an electron. So it's sodium, so it's always going to have 11 protons. But if I remove an electron, now I only have 10. What is the overall charge? I have 11 positives and 10 negatives, so I must have 1 positive left over. And so that's what I would write for my ion. Now, you could do this with any combination of protons and electrons. In fact, you could just do protons minus electrons will give you the charge. So if I had something like this, 11 minus 13 is negative 2. So this would be a sodium that has gained 2 electrons. Okay, so this is the answer for this problem. This is just an extra one that I did. All right, I want you to write the ion that forms when you add an electron to chlorine. Type that to the best of your ability in the chat. Is it safe to say electrons are like 1s or minus ones? Yes. Sorry, 1s is something different. We're going to talk about that in 161. But yeah, electrons are negative ones. Protons are positive ones. Very good. Cl minus is correct. And so I gave my chlorine an extra electron. There are now one more electron than protons. So the overall result is that I have Cl minus. Now, on the board, you can actually see the pictures are illustrated with size in mind here. So 11 protons and 11 electrons take up a certain amount of space. If I take away an electron, everything kind of gets shrunk in because there's fewer electrons repelling each other. Down here, adding an extra electron, I got to put it somewhere so everything expands to accommodate. So the size of an atom, we're going to talk about this in Chapter 8 a little bit, depends on the number of electrons that are present. So we'll mention that in much more detail in 161. Sorry, I didn't mean to scroll forward. Now, ions behave extremely differently than neutral atoms. So, for instance, sodium metal is explosive. And we saw this on the first day of class. I showed you a bunch of videos of the scientific method. Or more appropriately, you watched a bunch of videos for the lecture that I linked to you because I was in bed crying because my foot hurt so much. Now my foot is good, but remember back to that video that you saw on the lecture that I linked to you. Sodium metal was explosive in water, but sodium ions are very stable and in fact are shown in table salt is where we would find sodium ion. Does the mass change with different charges? Almost unnoticeably. Very, very, very small change in mass from moving electrons around because electrons are extremely small. We're going to assume electrons, for the purposes of this class, weigh 0. Because they almost do. All right. So for this discussion here, bananas are said to be a good source of potassium. How would you find potassium in your banana? Atomic potassium or ionic potassium? Obviously, the answer is this because we saw potassium explodes in water too. So eating bananas would be incredibly dangerous, or maybe it would be awesome if metallic potassium was present in your banana. Likely what would happen if metallic potassium was present in your banana is that the banana would burst into flames the second it was present, because bananas also have moisture in them too. All right, these are just more examples of what you can do to write symbols for description. So if I add 3 electrons to a nitrogen, there you go. If I remove 2 electrons from a calcium atom, there you go. So pretty straightforward. Can you count protons and electrons? Sure we can. So if I know that the charge is +2, and I know that iron must have a certain number of electrons, according to the number of protons, according to the periodic table, it's 26. How many electrons would it have? Well, it would have 2 fewer, right? So that would be iron with a 2+. So again, there's a bunch of different configurations of questions that I can ask you about parts of the atom. The most common one is going to be something that looks like this. This is where I want to stop. So I'm going to have you fill in this table to the best of your ability, and then we'll fill it in as the last thing we do today. So on this table, I want you to write the isotopic notation of the symbol represented by what you see. Include the charge on this notation. So, for example, right here, I would put the charge. You're going to need a periodic table to look up the number of protons. In the box that says element name, don't capitalize the element's name. Elements are not proper nouns, so leave them lowercase. That will be very important later on. When we do naming, Canvas will mark your answers wrong if you capitalize them inadvertently. So go ahead and fill out this table. Based on the information that is shown, we will go over the answers together in just a moment. Let's do 1 or 2 more minutes and we'll go over the answers here. All right, let's go over the answers. I got the periodic table out here. All right, so according to my periodic table, titanium has 22 protons, so we'll just fill that in. And so now I have all the other information. I can write the isotopic symbol. So 22 plus 24 is 46. And then if I have 2 fewer electrons, I would have a charge of 2 plus. So this would be a cation. I'll just put it over there because I don't know where else to put it. All right. For the second problem, I sort of go in the opposite direction. I give all the other information. So if this is Br, that means this is bromine. Here's Z, so we'll just fill that in. And then how many electrons? 35, and I have a 2 minus, so I have 2 additional electrons. Which makes it an anion. For the third one, this is the number of protons, so that means it must be carbon. Number of neutrons would be 7. Mass number would be protons plus neutrons, so 6 plus 7 is 13. 8 electrons is 2 more electrons than protons, so this is also an anion with a charge of -2. Down here for lead, there's Z. A is whatever the difference between these two is, so 205 minus 82 would be 5 minus 2 is 3, 20 minus 8 is 12. And then I have 4 fewer electrons than protons, so that'd be this. And it's positive, so it's a cation. And then finally down here, I make you do everything on your own. So this is ruthenium. Number of protons is 44. 94 minus 44 is 50. So that's the number of neutrons. 3 fewer electrons, which is a cation. All right, there you go. There's the answers. Let me know if you have any questions. And I believe that's where we're going to stop because, the next slide is doing calculations. We do need to do a little math in this section, so I'm going to save that for next week because, we have plenty of time. Chapter 8 is very short. This is a lesson on it that will take up like maybe an hour. So odds are like 100% that we will cover the first 8 units before the exam on the end of week 5. So we are right on track for where we need to be. I do want to thank everyone for coming out to the lecture. If you have any questions, let me know. Since we have done the discussion for lab number 2, I'm going to go put that assignment up right as soon as class is over and I finish up the last of the video stuff. Quiz number 2 is due tomorrow night, closes on Thursday. Quiz number 3 is due on Monday. Quiz number 4 will be due after the exam, but I'll recommend that you do it before then because there will be questions from the quiz on the exam, and I'll have it set so that you can get your answers immediately. So everything should be all set. We are right on track. Make sure that you're using the Discord to ask any questions you might have. That's kind of our office hour place. You can also private message me if you prefer. I've been answering a few questions that people have been asking out of the workbook, and they have been excellent questions so far. Please continue to do so, as you need to, in order to help you study. Okay? That's all. That's all I got. Have a wonderful rest of your evening, and I'll see you next week. And hit me up if you have any questions. Take care.